video, we're going to do a quick overview of what's called intermolecular forces. So you would have done the lesson using the video lessons, but this is another overview that goes over a few more details that you might need to know. So we've already discussed intramolecular forces or bonding forces, which are the forces within atoms that hold within molecules or substances that hold the atoms together. So if we take a look over here, we have the water molecule and these two bonds over here. These are intramolecular forces or bonding forces that hold the atoms of the water molecule together. And so the main types of intramolecular forces or bonding forces are the ionic, covalent, and metallic bonds. So what I want you to pay attention to here is just their relative strengths. You'll notice, for example, that they do range quite a bit. Like there's a low part to their range and a higher part to their range, which is what a range is. But you'll notice that ionic has a higher range, and then you have a pretty high range for covalent here, pretty high value, and then afterwards a little bit lower for metallic. But they are pretty strong compared to intermolecular forces. So we did review this in a previous lesson. Please make sure you go back and take a look. Don't forget that the intramolecular forces, since they are the strong ones, and they are the ones that are responsible for holding the atoms within a substance together, they will determine the chemical properties overall. And so when you do a chemical reaction or chemical change, you're actually breaking these intramolecular bonds. Now, our focus in this lesson is to review the intermolecular forces, the prefix being inter, think between different nations, like international. And so we sometimes call this IMF or non-bonding forces, and they're forces between separate, let's say, molecules that are not holding the atoms together within a molecule, but they're holding separate molecules together. So here we have, for example, water and another water molecule, and you have this force over here that's holding the two water molecules together. The partial positive hydrogen of one water is attracted to the partial negative oxygen of the other water. And that's considered an intermolecular force because it is between separate molecules. Overall, intermolecular forces are weaker than the intramolecular forces, and they require essentially less energy to break them. So they determine the physical properties of a substance. So for example, when we talk about things like boiling point, melting point, and so if something dissolves or not, it's really because of these intermolecular forces that we see here. So typically, because they're weaker, we represent them by these dashed or dotted lines or broken lines. And here is just a little bit of data to show you how weak an intermolecular force is compared to an intramolecular bond. So here we have water, liquid water, becoming gas water. And in the equation below, let's call this equation A, this equation B, we have water breaking down, decomposing into H2 and O2. So to do this one, to do B, you need to break these. To do A, you need to break, so we'll make A in red, you need to break these. Notice this is the amount of energy required to do A, to boil, to evaporate. And this is the amount of energy required to decompose. So you need a lot more energy to break those intramolecular covalent bonds than you would to break these intermolecular bonds over here, forces over here. And you might remember this between two water molecules. The specific name for it is called a hydrogen bond, or sometimes abbreviated to H bond. So intermolecular forces, there's many different types that exist. The ones we're going to focus on are the dipole-dipole, and some examples are hydrogen bonding. That's one example of a dipole-dipole. London dispersion forces, Ion-Dipole, Ion-Induced Dipole, and Dipole-Induced Dipole. But the main focus will really be London dispersion and the dipole-dipole with hydrogen bonding. So we're going to go and take a look at each one of these different types of intermolecular forces, and then afterwards we're going to take a look at what properties they help to determine within substances. So we'll start with the dipole-dipole, and that's when you have two molecules or more, when you have the partial negative end of one of the molecules attracted to the partial positive end of the other molecule. And this here would be a dipole-dipole interaction. And what that means is that in order for this dipole-dipole to happen with this partial negative and partial positive, you need to have polar molecules present. So you need polar molecules for this to happen. You'll notice this is a relative strength here. You don't need to memorize that, but that's the relative strength compared to, that's the strength energy-wise compared to If we look at our other values here for hydrogen bonding, for example, this has a higher value in its range overall compared to this one here. So you don't have to memorize these, but they are intermolecular forces. They're not the strongest intermolecular force, and we'll rank them later on, but the strength essentially is represented by the energy required to break them. So here we have another example. We have our partial positive carbon, our partial negative chlorine in this molecule. This partial negative chlorine is attracted to this partial positive carbon, and this is a dipole-dipole interaction. So if you have polar molecules, then you can have dipole-dipole interactions. Now, another type of intermolecular force is called a hydrogen bond. This is a type of dipole-dipole interaction. It is a dipole-dipole, but it's stronger than a regular dipole-dipole, so we give it its own name, call it the hydrogen bond. And how do you know when you can have it? Well, if you have polar molecules that have these special groups, HN, HF, HO, or HF, then generally you can have hydrogen bonding that happens. And that's because those special groups have a big electronegativity difference, so they're quite polar. Generally, the more polar the group is, the stronger the dipole-dipole can be. So if you have HN, HO, or HF, you have the potential for hydrogen bonds. So here we have two water molecules. This is a partial positive H of one water, partial negative O of another water. This is a dipole-dipole, but because it's between special groups of OH and OH here, we have a hydrogen bond happening. Here we have partial negative on ammonia, hydrogen bonding with a partial positive on another ammonia. And this would be another hydrogen bond. And here you can see the hydrogen bond between HF and HF. So just to clarify, don't think that just because you have hydrogen, it's a hydrogen bond. For example, if I have HCl and I have a intermolecular force between these two HCl's over here, this is partially negative, this is partially positive. This could only be classified as a dipole-dipole, not a hydrogen bond, because it doesn't have the special groups of HN, OH, or HF. So just keep that in mind. Again, these are still dipole-dipole, but they're a stronger version of the dipole-dipole that have these special groups. A trick we sometimes use to remember this is H just wants to have fun. So H with F, H with O, or H with N, special groups that allow for special types of dipole-dipole called hydrogen bonding. They're very weak compared to covalent bonds, 5% the strength of a covalent bond, but collectively when there's a lot of them, they do provide a lot of strength to water, a lot of the properties to water. So for example, water has a very high surface tension, we say, and so that surface tension means that the surface of the water is hard to break. So you can actually have insects that can sort of stride on water without breaking the surface, and that's because the hydrogen bonds are strong enough to prevent the insect from breaking the surface of the water. So even though they're weak, when there's a lot of them, they're strength in numbers. And here we can see again examples of hydrogen bond where you have the special groups. This dipole-dipole is a hydrogen bond. Special groups NH and OH, hydrogen bond. Typically, the hydrogen bond between OH and between OH is stronger than the hydrogen bond between NH. So if you see an OH-OH hydrogen bond, that's stronger than an NH-NH hydrogen bond. So it takes more energy to break it. And the hydrogen bond is the reason why water has such a high boiling point. Water boils at 100 degrees Celsius. That's pretty high for a small molecule. This is only 3 atoms big. If you think about it, CO2 is gas at room temperature. In fact, it becomes a gas in the negatives, negative 78 degrees Celsius. And it's only 3 atoms large. But it still has a very, very low boiling point. It becomes a gas very easily. What that basically means is that it's very easy to disrupt its intermolecular forces. Whereas water, 3 atoms large, boils at 100 degrees Celsius, it takes a lot of energy to disrupt these compared to what it would take to disrupt what CO2 has. So again, we can see that these intermolecular forces are going to play a big role in those properties like boiling, melting, and dissolving. So let's go into our question. Let's go and question, why is it that CO2 has such a low boiling point? Why does it become a gas so easily? What weak forces are holding it together? We're going to answer that shortly, but just keep this in mind. This is a planted seed for CO2 later on. Another intermolecular force that you'll sometimes discuss, especially when it comes to dissolving, is the ion-dipole. Ion-dipole is stronger than dipole-dipole or than hydrogen bond because it forms between a full charged ion and a dipole. And this you'll commonly see when you're dissolving. So you can see it's the attraction between an ion and a partial charge of a polar molecule. So you need an ion and a polar molecule. And you can see this is the strongest intermolecular force. We have a range of 40 to 600, and it depends on the polarity of what's interacting. That's why there's a range. But when you dissolve salt in water, for example, what's going to happen is the partial negative ends of the water are going to be attracted to the positive ion, the Na+. And this is an ion-dipole interaction, attraction between an ion and a dipole. The partial positive ends of the water, they would surround, if you were dissolving salt, the chloride ion, which is negative. And so these are ion-dipole interactions. And so we can see water dissolving over here. This is what's basically happening is we're taking some NaCl, putting it in water. So that's why I'm putting aqueous there, because it means we're putting it in the solution. And when it's in solution, it basically becomes Na plus dissolved and Cl minus dissolved. And that aqueous basically means what you see here. You have this negative charge surrounded by the partial positive H's all the way around. And these are all ion-dipole interactions. Ion-dipole interactions. And then here you have the positive charge. I don't know if I said positive accent here. Negative charge surrounded by partial positive. Here you have the positive ion surrounded by the partial negative oxygen. And essentially what happened is that water came in between the ions and surrounded them because there were some different attractions happening. Partial positive surrounds the negative. Partial negative surrounds the positive. And this is called a dissociation. So when water separates the ions during the dissolving process, that's called dissociation. So this is a dissociation equation shown over here. So I had planted the seed of the CO2. CO2 essentially being a gas at such a low temperature. And now we're going to see why that is. So one of the weakest intermolecular forces is the London dispersion force. I'll sometimes just call it LDF. The London dispersion force is very, very, very weak. It's the base force that exists in basically everything. So every substance that exists has London dispersion forces. It's the default. So for example, water, I'm not going to draw out the structure, but water has H bonds, hydrogen bonds, plus LDF. But its strongest force is the H bond, and that's what's responsible for determining its properties. So everything has a default LDF, and if you have other special groups, then you can have things above that, like hydrogen bonding or dipole-dipole, for example. So LDF is everywhere, but it's the only force for nonpolar substances. Nonpolar substances don't really have those permanent partial charges. So they can't form dipole-dipole, and they can't form hydrogen bond. The only thing they can form are the weak LDF. They are the weakest of the forces. You'll notice the highest they go to is about 40 kilojoules per mole. They are the weakest one. So how does an IMF form if there's no partial charges? Well, in reality, the electrons are kind of always moving around in an atom. Okay, they're always moving around. And so what happens is sometimes you'll have an electron cloud or density just because they're moving, just be more dense here compared to here. So I'll make a small little e here. And at those times, this part becomes partially negative and this part becomes partially positive. And what that is it's temporary. It doesn't last because the electrons keep moving around. So we call these little temporary, or sometimes we call them instantaneous dipole moments. They happen in all molecules because electrons constantly move around. So for brief moment of time, an atom that did not have partial charges will, just because the electrons move around. So you can see that here. And when that happens for a brief moment of time, it's going to be attracted to another molecule or substance that happened to. And that's going to be the LDF. But again, it's just temporary. It's instantaneous. It forms and breaks, forms and breaks, forms and breaks. And that's why it's so weak. But they are still forces that are there. And when there's a lot of them, they can contribute significantly to some of those physical properties we're going to discuss soon. So let's go take a look at LDF and how they can vary from molecule to molecule. So generally, what we notice is that as the mass of a molecule increases, the LDF also increases. So if you have a higher mass, generally it means you're a larger molecule, which means you have more electrons. Because if you're larger, you have more atoms. And if you have more atoms, each atom has more electrons. And so if you have more electrons, you have more LDF. So with more electrons, there's more London dispersion forces because you have more electrons moving around. You have more partial charges developing in an instant and then breaking and developing, breaking and developing. So if we take a look here, we have some samples. We have iodine, bromine, and chlorine. These are all at room temperature. You'll notice iodine at room temperature is a solid. It's hard to see here, but bromine is a liquid. And then here, chlorine is a gas. So these F2, Cl2, Br2, I2, they're all, that's a liquid, this is a solid, they're all nonpolar. Because they're all nonpolar, they don't have dipole-dipoles, they don't have hydrogen bonding. The only thing they can have is LDF. So that must be what's explaining the difference in their states at room temperature. And since I2 is a solid at room temperature, this probably has the strongest LDF holding it together, since it takes more energy to break up the LDF to melt or evaporate or whatever will happen to it. So the reason for that is if you look at I2 on your periodic table, it's the larger one. It has more electrons. If you look at the atomic number, it's a bigger atom altogether with more electrons. And so it's going to have more LDF. Followed by that is bromine. Doesn't have as many electrons as iodine, but it has more than chlorine and fluorine. And so because it has enough electrons to give it more LDF, it's going to be liquid rather than gas. And then these ones are pretty small, fewer electrons, so their LDFs are weaker. So they're all nonpolar. The difference must be caused by their LDF, which we know is caused by their difference in mass, because the iodine is the largest, has the most electrons, and then the rest get smaller and smaller and smaller and smaller. So it's important to understand that LDF can contribute overall to the properties, even though they're very, very weak. And so you can see some examples in this table over here. We have some gases, some noble gases, and you can see their boiling points, right? And you can see that, for example, helium is a pretty small boiling point, and then we have our Rn over here with 211, and that's a much higher boiling point. And so you can see that the reason is because of the mass. So these are all just atoms. They're not really molecules, and so you don't have polarity in atoms. So the only force these noble gases have is the LDF. That's it. So the difference in their boiling points must be due to LDF, and the one with the higher boiling point must have the higher LDF, and that's because of its size. More electrons, more LDF can develop. So there's another factor that can affect your LDF, and that's called shape. So I want to show you an example here. Here we have two molecules. These molecules here, it's hard to see right now, but they're actually made up of the same atoms. They're just connected in different ways. So these molecules are said to be isoelectronic to each other. What that means is they have the same number of electrons. And that essentially means that their LDF should be similar. If they have the same number of electrons, similar masses, right? Look at their masses. Those are masses there. They should have similar LDF. But you'll notice that it's probably not the case. These are non-polar molecules. How do I know that? Well, they're just CH bonds. When you see a bunch of CH bonds only, that basically means non-polar. So big molecules with only CH are non-polar in nature. So you'll notice that this one has a pretty low boiling point. This one has a higher boiling point. So you'll notice that this has probably more LDF. compared to this one, lower LDF. Even though they have the same number of electrons, this one has more LDF compared to this one here. So what factor explains that? Well, that's a factor of shape. Typically, if you have a linear molecule, like this one over here, the LDF will be stronger because you have more surface area to interact with another linear molecule like yourself. And so it can hold you together more effectively. You're holding it all the way around here. All these little lines I made, they're LDFs holding them together. Okay. Whereas a spherical molecule like this one here, the way it's shaped, really doesn't have as many point of contacts for LDF, fewer lines I drew there. So the shape can also affect the LDF strength. That's why the boiling point of pentane is higher than the boiling point of this 2,2-dimethyl propane, because it's a linear molecule with more points of interaction, greater surface area. So linear has stronger or more LDF points of contact compared to something that's spherically shaped. So lots of factors here can affect your physical properties. But if you take a look over here, we'll have this is a CH4. Then we increase the number of carbons, hydrogens every time. Notice the boiling point goes up. Right now, the shape for all of these is essentially linear. Notice the one that has a higher boiling point is this one over here. And that's because we're increasing the number of atoms as you get to butane. And so you have more LDF. So one factor affecting LDF is simply the number of atoms, the mass, larger mass, more LDF, usually higher boiling point. But sometimes, as we saw, you might have the same mass right here and here, but LDF can still vary. And that's because the shape can affect it as well. So spherical, not as many points of contact for LDF, whereas linear, more points of contact between the molecules for LDF leads to a higher boiling point. The last two intermolecular forces I briefly want to touch upon, we're not going to focus on them too much, are the ion-induced and then the dipole-induced dipole forces. So let's go over here. We have ion-induced dipole. That's where you have a nonpolar molecule generally. So here's a nonpolar molecule that normally does not have a dipole. There's normally no partial charges except for those little temporary instantaneous ones that develop. But sometimes what happens is there'll be an interaction where an ion will come by, and because it's charged, it will cause electrons in a nonpolar one to shift one direction or another. So for example, if you have a positive ion come by, it'll pull the electrons in this nonpolar substance towards the positive ion, and that creates a little bit of a dipole that wasn't there before. And so we call it ion-induced because the ion created a dipole where there was none before. And this kind of forms and breaks. It's not the strongest one because it's between an ion and a non-polar molecule where the dipole is not quite permanent. You can think of it almost like a stronger LDF in a way. And that's called an ion-induced dipole interaction. And sometimes you might have also what's called a dipole-induced dipole. So this is even weaker, but it's the same idea, where you have a polar molecule with a partial charge or partial charges interact with a non-polar molecule without partial charges. And when that happens, what it's going to do is it's going to cause electrons in the non-polar molecule to shift to one direction or another. So it might move, since we have a negative charge here, it might move the electrons away. So this way over here, and then less electrons here. So this becomes partially negative, partially positive for a bit, and they interact. And so this was a dipole that was created by a dipole rather than an ion. And that's another example of an intermolecular force. But again, we don't focus too much on these. We focus mostly on the ones that we mentioned above in grade 12 anyways. But again, here you can see the ion-induced dipole. This is our regular atom or substance. It's non-polar, no partial charges other than the temporary instantaneous ones that might develop. A cation comes by and causes electrons to spend a bit more time here next to it. So there's an attraction there. That's an ion dipole. Here it's the same idea, except it's a polar molecule that comes by. and it has partial charges, so partial positive here, partial negative there, and it causes electrons here to kind of spend more time here compared to here, and so they'll be interacting for a little bit there, and that's a dipole-induced dipole. So the dipole here was created by a dipole from a polar molecule. The dipole here was created by a cation, and so we call it an induced dipole, almost like stronger versions of LDF. So you should be able to predict what type of forces molecules will have. This is a great flow chart to help you make those predictions. This is stuff you've also seen in grade 11. But essentially, you ask yourselves these questions and you can figure out what forces are involved. So for example, if I have water and I want to figure out what are the forces involved in water, well, you can ask yourself the following questions. Are there ions present? Well, it's water. It's a molecular compound, so there are no ions. Are there polar molecules? Well, you have to figure out if water is polar or not. So yes, it is polar. Are there atoms bonded to N, O, or F? Yes, there are. There's OH, right? When you draw this out, there's OH. And so yes, there are. So that means there's hydrogen bonding. So water has hydrogen bonds plus LDF. Hydrogen bonds plus LDF. And then, if we had, let's say, CH4. So same idea, we're going to go through the questioning. Are there polar molecules present? Or are there ions present? No. Are there polar molecules? No. So since there's no polar molecules, this is all non-polar. The only thing this has is LDF. And so if you can identify the types of forces present in molecules, then you'll be in a good position to be able to predict properties of molecules, like their boiling points, their melting points, and also their solubility. You should also know the relative strength of these forces that we discussed. Typically, you'll have ion-dipole being the strongest, followed by H-bond, then regular dipole-dipole, then induced forces, and then LDF being the weakest. So know the relative order. This table shows you that order and their energies required to break them. So it kind of shows you the strength that you might see there, with dispersion being the weakest, ion-dipole being the strongest, H-bond not too far behind, dipole-dipole, and then your induced forces over here being just slightly stronger than the London dispersion forces. And so the strength of these intermolecular forces are going to determine those physical properties, or allow you to make predictions about those physical properties going forward. So, and also keep in mind that these intermolecular forces that we saw, they are weaker than the intramolecular bonds. They are weaker than intramolecular bonds. The intramolecular bonds are stronger, and they determine those chemical properties as opposed to physical properties. So in the next video, we're going to take a look at some of the properties that are determined by these intermolecular forces, and we're going to do some practice problems to be able to make predictions about properties for substances relative to each other.